Hello and welcome to the final episode of the Spring 2025 New York City Category Theory Seminar. And today we have Thiago Alexandre, talking about topological derivators. Anyways, this is part two of a very popular talk that he gave about a month and a half ago, 2 months ago. So take it away, Thiago.
Oh, thank you very much. It's a pleasure to finally finish this talk about topological derivators.
Yeah.
So I will I will start by just establishing some terminology about geometric morphisms and some an instance of geometric morphisms. So just recalling that geometric morphism between oh, okay. Geometric morphism between toposes or topoi is a couple of adjoint functors, right? And we have the phi up star, which is the inverse image or the inverse image component of phi, and phi down star, which is the direct image component of phi. And the geometric morphism is essential when its inverse image admits a left adjoint, which normally is denoted like this. And it's called the essential image of the essential image component of phi. But now what is important is that phi zetal, when it's of the form, it's of the essentially of this form here. So it's the projection of the common category with respect to some object v of the topos y. And the geometric morphism is called the geometric immersion when its direct image component is fully faithful, and a geometric surjection when its inverse image component reflects the isomorphism or is a conservative functor. So, and a warning is that for many authors, including Peter Johnston's, Olivia Caramello, actually almost everyone, a true arrow of in the true category of topoi is a natural transformation between the inverse image components of the geometric morphisms. However, in SJ4, where the top posterior was introduced by the first time, a true arrow as above is actually a natural transformation in the order direction. So I follow the orientation established at SJ4 only because it is more appropriate to theory of derivators over toposes. But we can it's just it is not a big deal. It is just an orientation of notation. You can translate everything that with these other direction. But I guess it is important to mention this because well, I have to dualize some categories that normally people don't dualize, but it's so. At my in my last talk, I said that derivators are Morita invariant. So in the sense that if two small categories have equivalent toposes of presheaves, then the derived category, the when we apply a derivator in each one of these categories, we achieve equivalent derived categories, right? Now, I actually there is a very I discovered after that there is a very elementary proof of this fact. And I would like to begin with this proof because it will be important for uh, some results that I'm going to present in the sequel. So I will begin with this lemma, which is not. All these proofs are elementary in the sense that they are straightforward. As you just have to follow the formulas. There is no trick, nothing like of this sort. So there is this first lemma, which says that if you have a functor between small categories, and assuming that we have, of course, a derivator d here, then these equivalents are we have these equivalent conditions. So this functor is fully faithful. The geometric morphism induced by in the between the respective toposes of presheaves is a geometric immersion. So for any derivator D of the main cat, the 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 sphincter, the homotopical left can extension with respect to D is fully faithful, or or for any derivator D of the main cat, the direct image, the right can extension, the homotopical right can extension with respect to D is fully faithful. So there is this characterization of fully faithful functors in terms of derivators also. So it's all this. It is not that difficult to prove. And there is a second lemma which says that now if you have a functor between small categories, we can prove that these three conditions here are equivalent. So first one is that this functor is surjective up to retract. So it means that for any object of B is a retract of an object of A through the functor U, right? So for any object B, small b of B, there is an object small a of A and a retract of this form. So a retract means that when we compose R with I, we have the identity of B. So this condition is equivalent to say that the geometric morphism induced at the level of topology of presheaves is a geometric surjection. And this is also equivalent to say that for any derivator D of the main cat, the functor, the inverse image functor, reflects the isomorphisms, is a conservative functor. So we also have this characterization sorry, of this of functors between small categories which are inducing a conservative functor at the level of derived categories with respect to every derivator. So now there is a third lemma which says that for any small category, we can construct the Caribbean envelope of A, right, which is the idempotent completion of A, and there is a fully faithful functor of A into this category. And this functor is also surjective up to retracts by construction. And moreover, we can even identify the Caribbean envelope. It can be represented as being the category of essential points of the topos of presheaves of A. So it's a way to recover in some sense the category, not the category, but the Caribbean envelope of a small category um, from its topos of presheaves. Okay, so now we have those lemmas. We can prove this theorem, which is a very interesting theorem that if you have a functor between small categories, then all these five conditions are equivalent. So the first condition means that the functor is fully faithful and surjective up to retract. The second condition that the geometric morphism induced at the level of presheaf toposes is a geometric immersion and a geometric surjection. But it is also equivalent to say that this geometric morphism is actually an equivalence of toposes, topoi. Um, or this is also equivalent to say that the functor induced, the universal functor induced at the level of Caribbean envelopes is an equivalence of categories. And most interesting is this five condition that for any derivator D, the functor, the inverse image induced at the level of derived categories with respect to D, of course, is an equivalence of categories. So there is this interesting characterization of Caribbean equivalence of categories in terms of derivators. These are precisely the functors which have equivalent categories here of derived categories with respect to every derivator D. And as a corollary, we have that if A and B.
Could you just give a 1 minute reminder or a half a minute reminder of what a caribou envelope is?
Yeah, basically, it's the idempotent completion of a small category, but conceptually, It is a way to recover if you want to, if you have a topos, for instance, um, and you know that it is a categorical topos, so it's a topos of sheaves.
Hmm.
How can we recover the category of the small category from this topos, right? The small categories for which the this topos is the topos of sheaves. So uh, when you do this, we you don't actually recover the. Of course, many categories can have the same equivalent toposes of Sheaf, but when you do this operation, you actually compute the essential points of the topos. So, and this is the Caribbean envelope, or this is one of the ways to present the Caribbean envelope. But another way is that it is the idempotent completion of A. So, in the sense that every idempotent morphism splits. So, and
Thank you.
there is there's
Thank you.
also this other characterization. Now, yes, and now there is this corollary which says that if you have two small categories, A and B, so we have these equivalent conditions, which says that they have equivalent toposes of sheaves, and they have equivalent derived categories with respect to any derivator of the main cat. So this is actually the motivation for extending any derivator to the entire two category of toposes. So that it's a sort of evidence that such an extension shall always exist, at least. Um, and now, in fact, thanks to these results, we can reformulate the theory of derivators in the following sense. You can form this two category here, top cat exclamation here, which is the two category of categorical topoi, which are topoi of Prishev type, and where morphisms are essential geometric morphisms, right? And now to give a derivator of the main cat is equivalent to give a true functor of this type here, which satisfy a list of axioms. So, and this list, we can translate each one of the axioms of derivators in terms of categorical topoi and essential geometric morphisms between them. So, and these are the axioms. So, these are basically the axioms of derivators, but here they are expressed just in terms of toposes, categorical toposes. So, the first one, which is the basically says that a derivator commutes with finite sums. It actually sends finite sums of topoi to products of derived categories, finite products. And the second axiom is the most interesting to realize what is the translation because it is related with the geometric theories in some sense somehow. Because it admits this version, so that for any geometric covering of categorical topoi, so a geometric covering just means that we consider the family of inverse image components of these geometric morphisms, we have a jointly conservative family of functors, right? So, but basically a derivator preserves this property. So if you have an essential geometric covering, then the family of functors of inverse images with respect to reflects the isomorphism. So jointly reflects the isomorphisms, right? So the third axiom, of course, that the existence of uh, direct homological images and direct homological images, or left can extensions and right can extensions for the inverse images. And the fourth axiom is just the Beck-Chevalier condition, which says that for any Cartesian square of categorical topoi, by Cartesian I mean this square is Cartesian in the two category of categorical topoi and essential geometric morphisms. And here psi and psi prime are étale geometric morphisms. Actually, we only need to admit to assume that psi is étale because we automatically have that if this square is Cartesian, then psi prime will be also étale. So and that's the usual the Beck-Chevalier exchange isomorphism, which helps to compute the inverse and direct the direct cohomological images in some sense. Now, okay, now so the theory of derivators is actually defined at the level of categorical toposes and essential geometric morphisms between them. But can we extend a little more, even further, this a derivator? And the answer is yes. We can actually extend to arbitrary geometric morphisms between categorical topoi in a essentially unique way. So now let top cat be the true category of categorical topoi and geometric morphism between them. Arbitrary geometric morphism between categorical toposes. So in what follows, I will show that there is a unique way to extend the derivator presented as above to a chief functor of this type. So how can we do this? So first, the third thing we have to interpret what is a geometric morphism between categorical topos. So if we have two small categories A and B, a geometric morphism phi, it corresponds in some sense to a functor uh, from B hat to A hat, commuting with colimits and finite limits. In particular, sorry, phi can be regarded as a distributor. There is this notion of or a profunctor. Some people say profunctor, but it can be regarded as a distributor, which is a functor of this type here. And here P denotes the category of small sets, which is the point topos. I use this notation to indicate to denote the category of small sets P. Uh, so we can, of course, there is a correspondence actually, an equivalence of categories between functors commuting with colimits of this form and distributors like this. And in particular, geometric morphisms correspond to certain functors commuting with colimits and hence to certain profunctors. Now, given uh, uh, for any distributor or profunctor, we can associate yes, we can associate a functor commuting with colimits of this form here, which is defined like this because if you have a functor commuting with colimits, it is completely determinate at the representable presheaves, right? So by Kohn extension. So, but the interesting point is that if you have a distributor, one can define a span, and it's a particular kind of span, which I call a Grothendieck correspondence. It's a Grothendieck correspondence because it is span. A span is like a diagram of this form, so there is no arrow connecting A and B, but there are arrows of this form here. And a third category, small category, which is connecting A and B here. So, and P, the projection P, is a Grothendieck fibration in the categorical sense of Grothendieck fibration. And Q here is a Grothendieck cofibration. So, so here we just take the co-integration and the Grothendieck integration, and after the the Grothendieck co-integration, which I denote with the single nabla, and then the integral, the usual integration. Okay, now for the previous correspondence, one can define a span of essential geometric morphisms between the toposes, and I and one can verify that. So sorry, now I'm assuming that we are starting from a functor commuting with colimits, right? Functor commuting with colimits of this from b hat to a hat. Now, and one can verify that any functor commuting with colimits will be presented this way here by using the Grothendieck uh, correspondences, right? The Grothendieck fibration, the Grothendieck cofibration. And it admits always admits an evident right. So it's just an exercise with joint functors, and we can verify this. So, in particular, any geometric morphism corresponds to a unique determinate Grothendieck correspondence of this sort, and we can verify that if B admits finite limits, in this case, then this Grothendieck correspondence comes from a geometric morphism exactly when the Grothendieck fibration associated here at this in the span, appearing in the span, is what we call a representably flat functor, which means that the essential image of this functor commutes with finite limits. So in this previous case, we can actually form two geometric morphisms from P phi here, from this projection. We have a geometric morphism from A hat to C hat phi, and the canonical geometric morphism associated to P, the P hat, right? And these are given by the adjoint couples, these adjoint couples here. Therefore, one can verify that there is an adjunction of geometric morphism in the two category, an adjunction in the two categorical sense, in the two category of categorical topoi. So from the previous considerations, there is a
Well, one second.
commutative.
So every morphism in top cat is a pair of morphisms, a pair of adjoint morphisms, and now you can have adjoint morphisms of adjoint morphisms,
Yeah, because every morphism is an adjoint. Yeah, is an adjoint couple.
right?
Uh, but there is the notion, the two categorical notion of adjoint arrows, like when which are basically we have the what's the name? I forgot now. The triangle, the triangle identities, right? So we can in every two category we can define we have the horizontal compositions,
Right.
and you can form the triangles and the two, if you have two one arrows in a two category, then they will be adjoint if the triangle identities are satisfied. So we have the units and the co-unit, two arrows, and the so in that sense that, but in the when in the case of geometric morphisms, this means just that we just need to verify that the inverse image component of the of one is left adjoint of the inverse image component of the other, which is precisely what is happening here because here this functor, the first coordinate here, is the left adjoint of this functor. And normally this adjoint pair does not define a geometric morphism, but here it does because this functor commutes with finite limits. It's representably flat. So that's the
So
reason why.
there's a three-way. There's a right adjoint of a right adjoint of a right adjoint. There's three, the upper star, lower star, and bang. And that gives you, okay. Well, okay, fine. Okay. Sorry. So you got to keep track. So every adjunction, you got to keep track of four maps.
Yeah. Every that's right. So so yeah, and but this means that our if you have we if we have a geometric morphism like this, can be factored. We can factor this geometric morphism in a canonical way as a geometric morphism here, which is given by a representably flat functor, and a geometric morphism here, which is essential because it is just a canonical geometric morphism given by a functor, a normal functor. So we can factorize any geometric morphism in this way. And in fact, here I show why, but uh, so this is a way to present a geometric morphism. But what is important about this is that if you have any two functor from top cat to cat, a contravariant, right? A true contravariant two functor, extending the our original derivator d, we necessarily have for our previous situation this formula here. So that the phi up star d is given by this composition, and its right adjoint is given by this composition here, and those functors are defined because here p this is just the direct homological image of the Grothendieck projection, which is a functor. So these functors are defined for d already. So, and we necessarily have this. And but okay, here I am assuming that B, this category B here, the category B, admits finite limits. If not, there is a construction that we could perform, which is the Cartesian envelope of a small category. So it's just the exact completion. And it's the can this construction can be characterized as the solution of the following universal problem. So this category is finitely complete. It has all finite limits. There is a fully faithful functor of A into its envelope, and for any finitely complete category C, so we have an equivalence of categories of this form. So, and here at the left, the domain, the source of this functor, which is defined by composition, is the category of left exact functors from the Cartesian envelope to C. So it's the finite completion of A. And from this Cartesian envelope, the Cartesian envelope of a small category, we can construct this topos here, which I denote like this, P of A. And it's called the free topos of A. Of course, that the fully faithful functor from A into its Cartesian envelope induces an essential geometric morphism, immersion, in this case, an essential geometric immersion like this, from the classifying topos, the topos of per-shifts of A, into its free topos. And therefore, we can define the fully faithful functor given by composition, where here h of A denotes the unit embedding, right? And here this functor is just the left-hand extension of the inclusion of A into its Cartesian envelope.
So,
So
so one second. I'm sorry. The so A of E of X has finite limits. and and if you take the hat of that, it's going to have all colimits.
Yeah.
But does it preserve all finite limits? Does it still have all finite limits?
Yeah, you mean the a hat of x?
The
The
A of I'm sorry, a, a x hat p of a it has
okay.
all it has all colimits because it's the hat, but does it have all finite? Does it retain all finite limits?
Oh yes, yeah. It retains. So because it is a per-sheaf category, so it is complete and co-complete. It has all finite limit, all limits and all small limits and all
So
small
what did you
co-limits.
gain by going from A to AX?
Yeah, that's the
A doesn't have A doesn't have all finite limits, or you're not assuming anything about A, okay? But AEX has finite limits, and AEX hat has all colimits and finite limits.
yeah. What you get is basically a universal property uh, which is which justifies this terminology of free tuples of calling P of A the free tuples of A. So that's precisely what is this the next slide uh, is saying because this tuples is a solution of the following universal problem. For any tuples T, we now have an equivalence, a canonical equivalence between here geometric morphism from T to the tuples to the free tuples of A and functors from A to T. So in a certain sense, it means that the free tuples classifies A index diagrams among toposes. So it is the how can I say it's a classifying topos if we want we can see that when we consider a index diagrams among toposes we are kind of considering a structure among toposes right a theory in some sense it is a kind of theory and what it means is that the free topos is the classifying topos of this theory and this universal property only holds for the free tuples and not for a hat, but for the free tuples. So we kind of have a
Well,
there is
where did
the
that homotopy come from? Um,
homotop. Ah no, here home top. Ah, I'm sorry. It's home top, not homotop. It's a mistake of mine. Yeah.
okay, so are you sure it's not cat top? Uh,
Sorry.
uh,
Here the source of this functor is the category of geometric morphism from the tuples T to the free tuples of A. Uh, uh, there is no O here. It's just
okay,
home
okay,
top, right?
okay,
So
okay.
I sometimes I denote like this the category of geometric morphism. So and just to mention here, I have to normally people don't dualize here. I just have to dualize because of the warning I gave at the beginning. So
Hmm.
no, but so that's the meaning of this construction of the free tuples. It's a very important construction. That's why I'm already telling it here because it classifies diagrams, the A index diagrams among topoi. So it is the construction of the classifying tuples of this geometric theory. The geometric theory, which is a derivator, right? It's a topological derivator. It's a derivator over toposes, which it takes a tuples and returns the category of functors of AI indexed diagrams in this tuples. So
Okay, good, good.
now, but this is also important for the to to analyze the case of a geometric morphism when the target uh, the target category here B is not necessarily um, finitely complete, because in the case of when it is finitely complete, we know exactly how to extend a derivator D to the geometric morphism, right? But if not, we can actually just compose. We can just take the immersion, just enter geometric immersion of B hat into P of B and to the free tuples of B to obtain a geometric morphism, a composed geometric morphism like this. And now it's very easy to verify that for any two-functor extending the derivator D, we necessarily have, for our previous situation, these formulas here. So the inverse image of psi with respect to D must be equivalent, must be isomorphic to this composition, and the direct image must be, which is the right adjoint of the psi, psi star up star, must be isomorphic to this composition here.
Yeah.
But
Okay,
notice that
Thiago, when you said before hamcat or ham tap, you meant tapcat
home
over
top,
here.
no, here is
So
home
what's the
top.
right? So what's the difference between a ham tap and tapcat?
Oh, okay. So no, top cat is the two
Topological
category.
category, a topos
Oh,
yeah. Sorry. You talk.
no, sorry. Just no. It's just that actually, top cat is the full subtree category of the category of toposes formed by only by categorical toposes, which are the toposes of presheaf type. And so the morphism here are just geometric morphism. Home top is just when I write the home top from a topos x for like home top for x to y, it's just a category of geometric morphism. So the from a
Oh,
topos to another one
okay. Sorry. Okay, good.
is the home category in the two category of toposes. But now what is interesting here is that we can see that these functors here they are uh, uh, defined only in terms of and sometimes of essential geometric morphisms, right? So and so these functors, these direct and inverse images are already defined for D. So this is the only way to do the extension. So I'm sorry, I think it's a little uh, it is not clear here all these arguments, but what I'm trying to show is at the end is this theorem here that for any derivator D of the main cat there is one and essentially only one way to extend D to a true functor of this type here from top cat to cat. Uh, we have seen that it was already true for when we are considering only essential geometric morphisms between categorical topoi, but now what I'm saying is that we can do the extension for categorical toposes and arbitrary geometric morphisms between them. So this is why, and we have the inverse and direct images, and they are completely determined by the restriction of the two cuts. So this is a very important result, which gives even more evidence to it's a kind of very important intermediary step to the extension of the derivator to all toposes. So this ends this first part of a very it's a very technical part but very important part of how we can actually so actually when we have anytime we have a derivator we automatically have this canonical extension to categorical toposes and geometric morphisms, or arbitrary geometric morphisms between categorical toposes. So, but now the hard part is how do we extend now D to arbitrary toposes? Because here I'm considering just categorical toposes. How do we construct the extension for arbitrary toposes and arbitrary geometric morphisms, right? So, as I said, Grothendieck conjectures in a letter to Thomasson that there is always one, and essentially only one way to do this extension. The idea of topological derivators, which I'm going uh, to talk a little bit more now, is that in some sense, somehow to impose some constraints, some conditions to the extension, which preserves enough, which kind of preserves enough the structure of the derivator to at least to uh, at least to for the to assert the uniqueness of the extension, at least perhaps the even the existence. So Hmm. so now okay, so topological prederivators before. So topological prederivators are actually defined in what I call topological true categories. These are full subtrue categories of the top, which is the true category of toposes, and closed under some constructions. So, for instance, I assume that every categorical topos, the true category of categorical topos, is included in T, our topological true category T. I assume that if X is a T, I call the objects of T topos now for now. So if X is a T topos and U is an object of X, then the comma, the local topos here is also a T topos. T is closed under products, so the product of two toposes uh, is also a T topos. Now here, this symbol denotes the product of X and Y, the toposes X and Y, in the true category of topoi, and not it is not the categorical topos product, right? It's not X Cartesian a Y. It is the category of sheaves over X with values in Y, or vice versa. The product in the true category of toposes is very hard to understand, very hard to work with, unfortunately. But actually, the categorical topos corresponds to the sum in the true category of toposes, which is it is what it is. But it's so that's why I use this all the symbols to denote the product and the sum, because the sum is actually the product of categories of the toposes considered as categories, right? So in practice, T stands for the entire true category of toposes, the true category of toposes with enough points, or the true category of locally connected toposes. And as I said, an object of T would be called a T topos. Sorry. Ah, oh, it was just so an object of T would be called T topos. And so these topological true categories are the the standard domains for topological prederivators and topological derivators. So a topological prederivators is the over a topological true category T is just a true functor of this type, right? And so for any topological true category, the collection of all topological prederivators of domain T forms a true category that can be denoted like this. where one arrows are just the pseudo natural transformations and two arrows are modifications. So given two objects, I would denote by this symbol the category of morphisms of topological prederivators of this type from D to D prime. And now we have a lot of examples. So for HT tuples E, we can associate the following at least two let's say two canonical topological prederivators. The first one is just this, which assigns to each tuples X assigns each tuples X with the category of geometric morphisms from X to E. So, and the other one assigns each tuples X with the product of X with E, the topological product, let's say, because it's the product in the two category of tuples. So the topological product. We have these two natural topological derivators associated to each t tuples E. Now, some very important propositions that are not hard to verify, but very important is that for any topological pre-derivator D of domain T, uh, we have that this factor here, which so T of X is the representable, right? This is just the representable topological pre-derivator associated to E. So this is sort of Yoneda lemma here, which says that the category homotopy here is the category of morphisms of between this from this topological prederivator to D, which is this topological prederivator. So this functor is an equivalence of categories. That's the Yoneda lemma for topological prederivators. And and as a corollary, we have that for any couple of theta poses, we have an equivalence of categories of this form. So
One second, one
morphism
second.
of
I'm missing you. Go up the slides and down the side.
this one
No, I
or the
don't see
other.
any slide. Everyone else got the slide? Maybe it's
Well,
just me.
the slide is missing.
This one is.
It's coming in for us.
Okay, sorry. So you go on.
So it's just one slide. Oh, okay.
Okay.
But which one is the slide of the corollary or the Yoneda lemma? Okay, okay,
No, no, it's me. It's not everyone else. So you just continue.
okay. So here we have this as a corollary, we have this equivalence of categories, right? And actually, we can say that these representable topological prederivators are just the geometric theories, right? In the logical sense, from the logical perspective, they correspond to the topological prederivators given by a geometric theory, which sends each topos. So, for instance, if you have a geometric theory T, these representable topological prederivators are precisely the topological prederivators associated to geometric theories, which sends each topos X to the category of T mod X, right? The category of models of T in the topos X. So these are precisely the so a topological prederivator is called representable or a geometric theory when it is precisely when it is equivalent to a topological prederivator of this form for some T tuples E. So um, more precisely, Z is representable when there exists a couple E omega formed by a T tuples E and an object omega of the E. such that for every t tuples x, this functor here, which evaluates, right? Evaluates takes the pullback of omega with respect to a geometric morphism phi from x to e. This functor is an equivalence of categories. So, and when it happens, when D is of this form, we say this couple is essentially unique. So, so if D is representable or a geometric theory, it is representable by a couple E omega, then E is unique up to equivalence and omega is unique up to isomorphism, right? So for this reason, E can be called the classifying topos. Of course, there can be more than one, but they are all canonically equivalent. But will be called the classifying topos of D, while omega will be called generic D coefficient. It's the generic because all other D coefficients, all other objects in D of X for some topos X are generated by omega through geometric morphisms, right? With target E. So, so I have a lot of examples of topological pre-derivators, and it already shows this very basic example already shows how the theory of topological pre-derivators is very connected with first-order categorical logic in some sense, because, as is said, these are precisely the topological pre-derivators given by models, internal models, right, of geometric theory, or a geometric sketch if you want, or even if um, this is the case, for instance, of Lavoisier theories and many other examples. Basically, every essentially algebraic theory is of this sort. You can internalize in a tuple. So in some sense, the problem of extending this already tells us that the problem of extending a derivator is somehow related to the problem of construct internal models of structures and even homotopical structures in some sense. There is this notion, which is very important, that a tuples E is called exponentiable when the topological pre-derivator given by the product, right? There is also this one which sends a tuples X to the product of X with E. When this topological pre-derivator is representable. So in this case, there is a tuples O of E, OE like this, which denotes the classifying tuples of. This tuples can be seen as can be regarded as the dual tuples of E in some sense. But not every tuples is exponentiable. Actually, there is a paper of Johnson which characterizes the main result of this paper is a characterization of exponentiable tuples. But every for instance, every locally finitely presentable tuples is exponentiable. I'm going to. So for instance, for any small category A, we have these natural equivalences. We have that we can construct the free tuples of A op, right? The dual category of A here. I'm sorry, I'm using just all instead of op to denote the dual category here, um, but I hope this is not a problem. But we have these equivalence, this canonical equivalence, natural and canonical equivalence of categories. So the product, the topological product of a tuples with a hat is equivalent to the category of presheaps over A with values in X. And this is also equivalent to the category of geometric morphisms from X with values in this three tuples. So this is the importance of the three tuples. So so therefore A hat is always exponentiable, and all A here is the three tuples of the dual category of A, the dual of A. For instance, if A is the point category, E, the category of just one object and one arrow, then we can define the tuples O, which will be, we can verify that in this case, it's just a category of functors from the category of finite sets to the category of sets. So with the previous notations, there are natural equivalents of this form. So the category of X is actually equivalent to the category of geometric morphisms from X to O, to this topos of. So this is the topos classifying the theory of objects, I guess it is in some sense. So it can be or classifying sheaves, right? But more generally, if you anytime we have a locally finitely presentable category, we can form the category of A-valued sheaves over any topos, right? So if we have, this is a case for groups, abelian groups, monoids, categories, groupoids, everything of algebraic nature in some sense. We can form the category of A-valued sheaves. And we can construct the full subcategory of A spanned by the Aleph zero presentable or the compact objects, right? And we can form this topos here. The topos of functors from this category is essentially small. It has a small skeleton, and we can form this topos from A Aleph0 to P to the category of sets. And this is the classifying topos of A in the sense that this topos classifies A-valued sheaves. So there are natural equivalents of this. We can verify that there are natural equivalents of this form here. So the category of A-valued sheaves is equivalent to the category of left exact functors from A Lf0 dual to X. And it is also equivalent to the category of geometric morphisms from X to this to this topos OA here. So this map, which assigns a topos X to the category of A-valued sheaves, it defines a representable topological prederivator. It is given by geometric theory. And it's a very important example because it, it it's it contains all the category of sheaves of uh, among toposes that we would like to consider, like sheaves of groups, group value sheaves, monoid sheaves, lambda module sheaves, so on. But there is a theorem very important theorem characterizing. This is the final theorem about topological derivators, which characterize when somehow it characterizes this representable topological prederivators, and it's a theorem. It appears in a paper of Olivia Caramello, and in this paper actually D is assumed to be here. So in this theorem, D is assumed to be the topological prederivator of sigma structures for signature sigma structures for a signature sigma. So L structures for a first order language L. But what is important is that for me here is this third condition, which appears again, which appears the notion of geometric covering. So so if we read this third condition, it says that somehow we can test for geometric, let's say geometric constructions. We can test if something it is belongs to the is an object of we want to of I mean, it's an object of the derived category by verifying if it is an object of the derived category by pulling back with geometric morphism along the geometric covering. So this is the idea behind this. Okay, I'm not going to now topological derivators. But just to mention that this theorem is important to. It's very important when we have to give examples of topological derivators, when we want to construct topological derivators from model categories, for example. So that's why I put it here. It's a formal theorem, but it is very important for examples. Now, topological derivators, yeah. So just remembering that we have topological derivators are defined over the topological true categories, and we can always define the categorical restriction, right, of a topological prederivator because we have these inclusions here, and we can always define by restriction a two-factor of this kind, which will be called the categorical restriction of D. Now, the definition, I'm not going to repeat. I'm just we just consider as axioms for a topological derivator the axioms I I presented in the beginning, which are the translations of the axioms of derivators in terms of essential geometric morphisms between categorical toposes. But now we don't assume that our geometric morphisms are essential and that our toposes are necessarily categorical. We just consider arbitrary geometric morphisms between toposes, T toposes in this case, and we just rephrase the axioms as we so. But there is an important thing here, is that in the third axiom, I assume at least that if so the third axiom asserts the existence of the right adjoint, a direct homological image, right? Of any with respect of the phi star up star for any geometric morphism. But here I assume this extra condition that if phi is a geometric motion, then this direct image is fully faithful. Okay, so and this is also important to mention that the left-hand extensions, the direct homological images, I only assume the existence of them for in the case of essential geometric morphisms between categorical topoi. I would like to assume for essential geometric morphisms in general, but I don't know if it holds for very important. I don't know yet. I don't know yet if it is the case for all examples. At least for the examples I want to, the important examples then of topological derivators. But assuming this condition for essential geometric morphisms between categorical topoi, by using the other axioms, we can actually prove the existence of the direct homological image for many other essential geometric morphisms between toposes, not only toposes categorical between categorical toposes, but arbitrary toposes. So, and the fourth axiom is just the Beck-Chevalier condition. So now, so these are the axioms of right topological derivators. The precisely the axioms I I presented before, but now I drop the condition of being essential geometric morphisms between categorical toposes. I drop essential and categorical for geometric morphisms between toposes. So we can verify that if D is a topological derivator of domain T, then its categorical restriction is will be, of course, a derivator of domain cat. And and we can verify more. We can verify that if we have a topological prederivator, and if the categorical restriction is a derivator of domain cat, and it satisfies at least the axioms, the third and the fourth axiom, then D automatically satisfies the first and the the axiom of which asserts the existence of direct homological images, right? And the axiom, the second axiom can be reduced. We can be translated as follows. Is equivalent to say the following condition, so that for any geometric surjection of the topoi, this functor, the inverse image, reflects the isomorphism. So, um, basically, a derivator. So the idea is that we are computing. It gives you derived categories, right? And whenever it somehow it is respecting the structure of the true category of toposes. So if we have a geometric surjection, then the inverse image reflects is also conservative. This property of geometric surjections is being preserved by a topological derivator, and if we have a geometric immersion, then the right adjoint, the direct cohomological image, right, of the inverse image, it's fully faithful. So these conditions are being preserved by a derivator. So in some sense, D of X is a category of derived sheaves over X. So we are kind of preserving the idea that a topological derivator preserves this idea of sheaves, derived sheaves. Right? Now, well, there are many other propositions that we can derive from the axioms, which are formal consequences of the elementary formal consequences of the axioms. One of those is that if X is a T-topos with enough points, and we have a topological prederivator satisfying this in the derived category is an isomorphism exactly when oh my sorry exactly when the fiber, the pullback, is an isomorphism in D of P, right? And in the evaluation of the at the point topos for every point of the topos X. So we take every point C of the topos X. So basically it's a stalkwise way to see if an arrow F at the X is an isomorphism. We can if the pullback with respect to every point, right, is an isomorphism at the fundamental category. Yeah, there is a useful terminology for DFB. It's the fundamental category of the derivator T. So it will be an isomorphism here in D of X. And there is also this bar or Boolean localization principle, which says that basically if the topological derivator is satisfying the local conservative axiom, which is their top true, which is the conservativity with respect to geometric coverings, right? Then for every tuples X, there exists a geometric surjection such that E is a localic or Boolean tuples. And the inverse image, the derived inverse image, reflects the isomorphisms. So it is very interesting because this idea of Boolean localization principle, it appears already in, in the Joyal letter to Grothendieck, where Joyal shows how we can. I will mention this after, but how to construct the homotopy category, the local homotopy theory of 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 spaces in every topos to how do we build the model category structure for this by simply show objects, right? And this principle appears already there. It is remarked by Joyal that the local equivalences are satisfy the Boolean localization principle because they are given by a geometric construction. This is very important. The idea of geometric construction somehow. So okay, I'm going to there is this. We can construct the shift derivator, but this is just a technical, a very important result, but just a technical. Hmm. Okay, yeah, if A is a locally finitely presentable category, then the map which sends each tuples X to the category of A-valued sheaves or X defines a representable topological derivator. So here I'd like to there is uh, there is a we can see that I like to mention that if A is not locally finitely presentable, but locally presentable, but not locally finitely, just locally presentable category, then this map here defines a topological prederivator. And this topological prederivator satisfies all the axioms of topological derivators except for the local their top two, the local conservative axiom. So all the other axioms, let me come back here. Let me back to the axioms too. So except for this one, their top two, all the other axioms are satisfied when we take the topological prederivator of A-valued sheaves, but for A being locally presentable category, not only locally finitely presentable. So this is kind of so that's interesting, but and so yeah, this is a kind of a problem in some sense, I guess, for the axioms, but however, this is the conservative axiom, the local conservative axiom appearing for the main construction. So, uh, and another important thing is that this construction of taking A-valued sheaves, if the category is not locally presentable category, then we can't even construct the inverse images. It doesn't even define a topological prederivator because we don't know how to sheafify. Basically, we don't. So, uh, yeah, there is a point that this works for locally finitely presentable categories because locally finitely presentable categories have a good notion of sheafification for sheaves. That's another important comment here. Now, I like to say some words about the uniqueness of the extension of a derivator to a topological derivator. First, in the case of uh, for the true category for the topological true category of topoi with enough points, let's um, let's focus on this domain. So I will show that there is a unique way to extend a topological derivative. Sorry, there is at most one way to extend a derivator to a topological derivator for the domain of topoi with enough points. So for the domain of enough points, of topoi with enough points, in some sense, the Grothendieck conjecture is kind of true if we consider that our extensions are topological derivators, the uniqueness part. So, uh, so that's the theorem for. So let D be a derivator of domain cat. Then there is at most one way to extend D to a topological pre-derivator D of domain being the topoi with enough points, satisfying the axioms their top two and their top three. Actually, these two axioms, their top two and their top three, are enough to assure the uniqueness of the extension. Okay, so uh, let's I wrote here a proof sketch of this fact. It is not hard to see, but basically I try to be brief. But so the idea is that if you have a tuples with, so let's fix a tuples with x with enough points. So we can always consider a geometric merge of x into a categorical tuples E, right? Because this is one of the forms of Jiho theorem that every tuples admits a geometric immersion into a categorical tuples. So by their top three, the inverse image here, the derived inverse image of this geometric morphous immersion G is a reflection, right? Because it admits a fully faithful right adjoint, so it's a reflection, left reflective localization, reflection. In particular, it says we can see that this functor represents the strong localization of the E, the derived category of E. Just remembering that here E is a categorical tuple, so here D of E depends only on the categorical restriction of D. And this functor actually exhibits D of X as a localization, a strong localization of the E. With respect to the class of arrows W in the E, which are invertible by this functor, right? So, which means that an arrow F of the E belongs to W precisely when it's in the inverse image of F, the derived inverse image of F is an isomorphism in D of X. And D of X is actually equivalent to the localization of D of E with respect to W. Okay, so this follows from their top three, because their top three says that this factor is a left reflective localization. So on the other hand, since G is a geometric immersion, it induces a fully faithful functor of the category of points of X into the category of points of E, and we can consider the replete image of this functor. And the elements of the LG here will be called the G local points. So these are the points of E, which can be factored by a necessarily unique, in this case, point, uh, essentially unique, right? Essentially unique point, unique because uh, which can be factored by a essential, necessarily unique point of X. The the image of G basically induces this functor, which is fully faithful, and the replete image, the essential image of this functor, are precisely the points of E, which can be factored by by a necessarily unique point of X, like in this diagram here, right? Okay, so we can consider now the class the W prime, the class of arrows in D of E, such that the inverse image of F is an isomorphism in the fundamental category of P for every G local point of E, right? And now we can, by using now their top two, we can prove that W prime coincides with W, or our original class of arrows W. But now the G local points are geometric morphisms between categorical topoi, right? Because P is a categorical topos, is the category of sets, which is the category of perceives over the point category, and is a categorical topos by hypothesis. So and in virtue of the theorem two, which I proved, which I uh, I I sketched the proof at the beginning. There is one, and essentially only one way to extend D to a true functor of this type from top cat to cat. And in particular, the derived inverse images of Xi of the which are induced by the G local points of E, they are completely determined by D, by the categorical restriction of D right here. So it follows from the previous reasoning that D of X is equivalent to the localization of D of E with respect to W, but W is equal to W prime, which is defined just in terms of the categorical restriction of of D. So so because so we have this, and W is completely determined by D via its unique existent expansion to the domain of top cat. This bibliograph D here is the categorical restriction of the bold D here, right? So we can even assume here that E is of the form A hat for some small category admitting finite limits, and we can, and in this case, each G local point of A hat corresponds to a Grothendieck correspondence, as I said before, and therefore we necessarily have this characterization of the Xi of star, the inverse image of Xi, and okay, so we can define the class of arrow, this class of arrows F in D of A, such that okay, this function here is invertible at the fundamental category, and we can at the end, we can see that if D satisfies their top two and their top three, then it follows from the general theory of reflective localizations that D of X is necessarily equivalent to the full subcategory of D of A formed by the WG local objects in D of A, which are the objects F of D of A, such that for any arrow in this, which lies in this class of WG here, this map is a bijection. So we have a uh, very, at the end, we have a very concrete characterization of what D of X must be, just in terms of the categorical restriction of D, right? Because here to define this data here, WG, DA, we are just using the categorical restriction of D. So, and D of X is necessarily equivalent to this category of the category of this to this full subcategory of D of A. We know exactly what the full subcategory is. And of course, here I'm considering that D is an arbitrary topological derivator, verifying the for which the axioms their top two and their top three can be verified. So, and we have it necessarily is equivalent to this category of these WG local objects in D of A. So so there is only one way, essentially one way, right? Because any way that you can any extension, any topological extension, let's say, of the derivator D, if this topological extension, for any topological extension, if this topological extension satisfies the axioms that are top two and they're top three, then it is absolutely determined, right? It is necessarily of this form. So there is a unique way to. So uh, we can say that the uniqueness, the uniqueness part of the Grothendieck conjecture is true, at least for the domain of topoi with enough points, and by assuming that our extension satisfies the axioms that are top two and that are top three. In particular, if the extension is a topological derivator, which satisfies these axioms, then there is only one way to extend a derivator to a topological derivator over the domain of topoi with enough points. I'm sorry, there is at most one way. Of course, the extension may not exist. I'm not saying that there is an extension. If there is an extension, it is essentially unique. So for the domain of topoi with enough points, not for the entire true category of toposes. For the entire true category of toposes, what I could prove is that is that actually this theorem 5 here, that if there is at most one way to extend D to the domain of localic or Boolean topoids, then there is at most one way to extend D to a topological derivator D of the main top for the entire true category of toposes. Satisfying the axioms their top two and their top three. So, in other words, a topological derivator D of the main top for the whole true category of toposes is completely determined by its categorical and localic restrictions and somehow. So, if two topological derivators agree for the domain of categorical toposes and for the domain of localic toposes, which are tuples of sheaves over locales, then they agree for the entire domain of toposes. They agree for all toposes. That's what this theorem 5 is claims. And the proof.
Thiago, how much longer do you have?
I'm almost finishing, I guess.
Oh, okay.
But I can conclude after this theorem because it's a the
Okay, just go on.
okay. So, but basically, we can reproduce the same arguments we did here for the case of topoi with enough points. But now we can replace points by geometric surjections such that the source E is a localic or Boolean topos. And we can do basically the same argument because the axioms their top two and their top three combined, right? They are basically just saying that our our topological derivator it preserves the shift structure, let's say because it sends geometric surjections to functors which are conservative, right? The inverse to adjunctions for which the left adjoint is a conservative functor, which is precisely the definition of geometric surjection. The inverse image component is conservative. Yeah, on the other hand, the axiom there top three just says that asserts that a derivator D over toposes preserves the fact that the direct image component is fully faithful for geometric immersion, for geometric immersion. So these are the only things that, and these are quite reasonable assumptions actually. These are expected the properties, right? Um, so we don't even need all the other axioms of topological derivators. We just need these axioms to to grant the uniqueness of the extension for the domain of topoi with enough points, and to grant that for the entire two category of toposes, thus this topological derivator is completely determined for the by its categorical restriction, of course, to its restriction over categorical toposes, and to its restriction over localic or Boolean, even Boolean toposes here. We can even assume Boolean toposes. So there are more. There is one more thing about the topological derivator hot here, but I'm not going to into this here. I think it's a good moment to conclude. So as a conclusion, just mention the three main results. So if we have the derivator of domain cat, so there is one, and essentially only one way to extend D to a two functor of this type, and and this functor for if we have a geometric morphism between categorical toposes, this functor returns an adjunction, right? Uh, so the second axiom is that there is at most one way, because I don't know if there exists always if there always exists, but there is at most one way to extend. Oh, it's miss. There is something missing. Yeah, okay. So there is at most one way to extend D to a topological derivator defined over the domain of topoi with enough points for. So for the domain of enough point topoi with enough points, there is a the uniqueness is proved for a topological derivative. There is only one way to. There is at most one. Sorry. And the third tier important theorem is that a topological derivator is completely determined by its categorical and localic restrictions or Boolean restrictions, the restriction to Boolean toposes. So in that sense, right, if two topological derivators coincide at these domains, then they are equivalent. So thank you very much. This is all. The, yeah.
One second, back up. The one slide.
This one?
Yeah. That's. I mean, this is the summary of the whole talk. So that's. Anyways, very nice, very nice. I have no questions. Anybody have any questions? Anybody? Anyways, Thiago, thank you very much.
Thank
It
you
was a
very
great
much.
talk. It was a great two talks. So this is like a result that people thought was true, or Grothendieck thought was true, and you finally showed it's true.
Yeah, so at least for Topoi with enough points.
Yeah. All right. Very nice.
So,
Anyways, ladies and gentlemen, this is the last talk of this season. We will see you again in September. Say hello to Miriam. Okay.
hello.
And thank you, Thiago. Stay in touch.
Thank you very much. Thank you very
All
much.
right. Okay,
Bye.
doke. Okay, everybody, thank you, and I'll see you in September. Take care.
See you.
A second, I
Bye.
gotta stop.